So in my talk, the aspect of long-rangeness will come in due to the buildup of long-range entanglement. And we will see that this long-range entanglement will lead to entanglement dynamics that is kind of different from what we are used to, namely after the initial increase of entanglement entropy in a kind of non-equilibrium situation, the entanglement entropy will decrease again. And this is basically a realization of a kind of a conventional quantum many-body system of the Page curve, which has been discussed extensively in black hole physics. And this brings me to the subtitle of this talk, Why Black Holes Are Tidier Than Children. And I will explain this as we go along. Okay, so first of all, now Marcus, pay attention, here comes your question. So the problem with a capital P for all parents. So this is the desired state of a kid's room. This is what you sometimes find. And now you think of this as a closed, isolated system with children inside. You just don't see them in the photo. And now the question is, can you identify which photo becomes before the other? Marcus, the experienced parent, will tell you immediately he can identify the error of time. This is before this. And going from here to here happens on cosmological timescales if children remain isolated in this kids' room. The only way to go from here to here is to bring the parents in there as well. Actually, if you Google for preparing a talk for like messy kids' room, then you find all kinds of tips of how you can actually go from here to here, kind of the other direction, but they all involve bringing parents in there and give you tips of how to do this without losing your own mind. So the question that all parents ask themselves is, how do you reconcile the second law of thermodynamics, or the error of time, with microscopic time reversal invariance? Or if you are not a theoretical physicist, you can ask the question somewhat differently. If you can take the thing out of the shelf, why can't you put it back into the shelf? So, okay, this question has bothered physicists for a long time, very somewhat differently, and it's basically the content of the second law of thermodynamics. And Boltzmann famously proved that the entropy of an isolated system is a non-decreasing function as a function of time. It's non-decreasing as a function of time. And what he basically claimed is that he has proven this using the Boltzmann equation. Well, Loschmidt famously objected to this and mentioned, well, if you kind of invert all the velocities, then you must go back to your initial state. So you cannot single out the direction of time if the underlying laws of nature are time reversal invariant. And the answer attributed to Boltzmann is then try to do it. And this is a very insightful answer and has been explained in a bit more detail by Thomson, which you know as Lord Kelvin. And basically the statement is simply, yes, so systems equilibrate. I mean, think of a gas that is initially in half of the volume and then expands into the full volume. So if you invert all the velocities, yes, you will go back to the initial state, but if you make any small error in doing that, you will not go back to the initial state. So in principle, you can have situations where the entropy decreases, but that requires incredible fine-tuning. And so here's just a numerical experiment that demonstrates this. So here, this is just basically particles that are interacting with some Lagrange-Jones potential with some random velocities. And then at a certain time, you invert all the velocities. So if you do this accurately, you should go back to the initial state. And basically, the time where you reverse the velocities, that's this time t a, t b, d c, t d. And if you do this with floating point numerics, so this is h of t, which is minus s of t. That's the quantity that Boltzmann actually used. So you see the entropy goes up, increases. And then if you invert the velocities kind of early here, then you go back to your initial state, even with floating point numerics. However, if you wait longer, there's no way you go back, yeah, because just the accumulation of errors makes it impossible. If you use bit numerics, so without any errors, then you always go back to the initial state. So the goal of this talk is to basically show you a class of models where you have actually a robust decrease of the entanglement entropy that's not fine-tuned. And what's going to be responsible for this behavior is the buildup of long-range entanglement as a function of time. Okay, so first of all, I'm just going to quickly remind you of what the generic behavior of the entanglement entropy is and contrast that with the page curve and where the page curve comes from. Then I'll introduce this model, which is kind of stands for other systems that show this kind of behavior, give you some results, and then also say something about the properties of these states that one generates here. That's kind of unusual, I think. And then also briefly say something about interacting systems. This is work done in a collaboration with a PhD student of mine. So first of all, what's the generic behavior of the entanglement entropy after, let's say, a quench? This has been explained to us by Calabrese and Cardi. So what you have is you can think of as that the quench starts creating quasi-particle pairs originating from the same point. Therefore, they are generally entangled. And if they propagate ballistically as a function of time, this entangled pair is going to entangle the regions A and B that you have over here. And this will basically lead to a linear growth of the entanglement entropy initially, which is, of course, what you also see numerically. Then if you wait long enough, at some point, if you look at a particle pair that's produced here, then you will see that it doesn't end up in the region A anymore. So it doesn't contribute to entangling these two regions anymore. So then you saturate, and you saturate at some volume law that depends on the smaller of these two subsystems, A and B. And this kind of behavior is generically also seen in, let's say, many body localized systems, except that the growth of the entanglement entropy is logarithmic, or even if you have diffusive energy transport, you see this kind of behavior. But this is what we typically have. Now there's one class of systems where the question of whether the entanglement entropy behaves like this or not has been the subject of debate that's been going on for a very long time, and that's in black hole physics. Just a brief kind of introduction to this. These are pictures taken from this recent review, Myriad al. So here you see the curved space-time due to a collapsing star that is going to form a black hole. And this red circle here is the event horizon. And then, as Hawking famously calculated, at the event horizon, you have virtual particle pair production with one particle going out into the kind of the outside. And that's what we observe as thermal black body radiation with the Hawking temperature, and the other particle falling into the singularity and actually decreasing the mass of the black hole so that overall energy remains conserved. But this means that the black hole as a function of time will get smaller and smaller, less and less massive, until it eventually all disappears, and the only thing that's left is the radiation. Okay, now where's the problem? One way of seeing the problem here is due to Page, and the argument is pretty simple. So let's imagine, to simplify things, that initially we're dealing with a pure state. So the pure state, of course, the total entanglement entropy of black hole and radiation is going to be is zero, which means that the entanglement entropy of the black hole or of the radiation part, they have to be equal. They will be equal at all times. Yeah? Because overall the system is in the pure state. Now we know that the entanglement entropy is going to be bounded by the dimension of the smaller of the two Hilbert spaces. So now, so initially, this was Hawking's famous calculation. Initially, the entanglement entropy is basically just going to be proportional to the particle pair production at the event horizon. It will go up, entanglement entropy will grow. But at the same time, the mass of the black hole becomes smaller. So the thermodynamic entropy becomes smaller. And the entanglement entropy can never become larger than the thermodynamic entropy. It's just that, think of it in terms of qubits. You don't have enough qubits anymore to catch all the entanglement at a certain point. So at some point, these two lines are going to meet. This is the page time. And unitarity basically tells us that the entanglement entropy has to bend down again. And there is no indication of this whatsoever in Hawking's calculation. Yeah? Hawking's calculation just tells us this goes up, it continues to grow linearly. And the issue is that this basically this page time, this is typically a time where the black hole has decayed to about half its original mass, so it's still pretty big. The curvature at the event horizon is not huge. You're very far away from the Planck scale, where you know that you don't understand the physics. So something goes wrong at a scale where we believe that we understand physics. Yeah? So it's not like a late time problem, it's a fairly early time problem. And this is why people have been, people in this community, this black hole community, have been trying to resolve this for a long time. And there have been all kinds of proposals, non-unitarity firewalls, island formula, non-isometric codes, and so on. I think nowadays people believe that they are kind of getting close to understanding what's going on here. Okay, so this is the page curve, and as a disclaimer, I want to say that I'm not going to claim that I contribute in any way to understanding black holes. So what I've been doing is I've taken this idea of a page curve and trying to see how one can model this in a simple quantum many-body system. And the setup is actually very easy. So this is just electrons, fermions hopping along a one-dimensional chain. You can generalize this. And the first M lattice sites I designate as the system, and the rest with many, many more sites. That's the environment. That's my environment. And I have some coupling across this boundary between system and environment, and that coupling should be smaller than the hopping matrix elements. Okay, so the initial state of the system is that, initial state of this this setup is that the system is full, so they have particles on all lattice sites, and the environment is completely empty. Then if you switch on basically this coupling, then what's going to happen is that the system is going to decay into the environment. Yeah? It's going to empty into the environment. And you can think of this basically a particle going out, a hole going in. This is basically like particle hole production at the boundary. So you have a constant buildup of a current across this boundary. And this particle current across the boundary will generate entanglement between system and environment. Now, why would one expect the page curve? Well, pretty straightforward. We start in a pure state, which always remains a pure state, which means that the entanglement entropy of either the environment or of the system, they're always going to be equal for all times. Now, if we, of course, the dimension of the Hilbert space of the system is always the same. The number of lattice sites there is always the same. But effectively, the number of particles that are sitting in there is going to become smaller as a function of time, because it's going to empty into the environment until it's completely empty if the environment is much larger. Now, if you ask the question, what's the dimension of the Hilbert space with m lattice sites, if you know that there's a given number of m of t particles in it, well, that basically dimension looks like this. Yeah, because if it's completely full, there's only one state. If it's completely empty, there's only one state. And the maximum number of states is when it's half full. So from this, you would already expect, because this basically will be a bound on the entanglement entropy. So from this, you would already expect that the entanglement entropy will go up and will go down again. This argument is not quite rigorous because we are neglecting fluctuations of m of t. But it gives you a pretty good hint that this should work. And kind of the advantage of this very simple system is that you can calculate everything numerically or analytically for very large systems, basically using a formalism that goes back to Pesher and Eisler. You just need the two-point correlation function. And from that, you can calculate the full reduced density matrix. Even I can do this without asking my students for help. So for about 10,000 lattice sites. Yeah.
Probably here, the behavior that you're going to get is going to depend a lot on the initial state that you have to.
So I'll come back to this a bit later, but you will always observe this kind of behavior, even if you are initially not completely full. You will always get this, except that the maximum value that you reach will be different. The shape of the curve can be a bit different. And for example, you could reach the maximum of the curve faster than here, because of the total time evolution.
So yeah, maybe what I'm saying is that it will go up and down, but maybe we go up with the log of whatever the system as opposed to with the volume of the system.
Oh no, you'll see that. It will be proportional to T.
Okay.
You'll see that. I'll show that to you. I'll show that to you, yeah. Yeah. Okay, so because the system is so simple, one can also analyze it analytically, specifically in the weak tunneling limit, where this coupling across the boundary is much more than the hopping matrix elements, because you can basically think of this, I'm diagonalizing my system. So what I have is basically it's like a resonant level model that's coupled to some environment with some hybridization. And this, the hybridization is very small if G is small, and therefore kind of the coupling is only to modes that are nearly energy degenerate in the environment, and they don't overlap for different levels of the system, and therefore I can just separate this into basically M disjoint resonant levels models that don't talk to one another. And for them, it's easy to work out the dynamics. So basically, this gives you analytical expressions in the thermodynamic limit that are fairly straightforward. Okay, so now these are just first of all the numerical results. Always for these parameters here, and this is the entanglement entropy now normalized with the size of the system, and the curves are basically T is divided by again the size of the system, and you can see that this looks reasonably universal for different sizes of the initial system if you scale like this. Over here is the same on the logarithmic scale, so you can see again, you can see better how it goes down to 0.
Sorry,
yep.
What is G?
G is the coupling system to environment. So it's basically the hopping across the boundary. Yeah, and you want it to be smaller than these. If you choose these identical and you choose G also identical, you actually have a logarithmic increase of the entanglement entropy. But this is one singular point, yeah, and I need to stay away from that point, yeah, right, okay. Or was that your question before? Oh, yeah, okay, so I'm staying away from the singular point, yeah. I'm going in the weak tunneling limits, yeah, yeah, okay. So you see that basically the page time, so the maximum is proportional to the size of the system. And the entanglement entropy at that point is also proportional to the size of the system, just as what you want. But what you can also see is if you look at the behavior of the number of particles that remain in the system, they just decay and there's nothing at all happening at this time. There's no indication of anything happening at this point in time where the entanglement entropy starts going down again. So this shows you that the semi-classical picture that basically says there's a proportionality between the particle current across the boundary here and the production of entanglement completely breaks down. Yeah. Okay. So kind of a better way to plot this is where it becomes really universal is as a function of the fraction of the number of particles that have been emitted into the environment. Yeah. So basically here, nothing has happened, and here, all the particles have gone into the environment. And this is now for different couplings, so for system and environment. So this is the kind of a small coupling, the weak coupling limit. And this is this analytical model, the resonant level model, disjoint resonant level models. And you can see, well, that this approaches this limit, this analytical expression reasonably well. And indeed, it goes up and it goes down And you find the same behavior if you look at the purity. This is the purity, and this would be the min entropy, so that Q equals infinity Rayleigh entropy. And here you can also really nicely see that the structure becomes very sharp. So there's no indication. Looking at short times, you get no indication that anything might happen at this point. Okay. Now, in a way, from the system point of view, this is nearly trivial. You empty your system, yeah? Entanglement entropy eventually needs to go down. However, now take the point of view of someone standing in the environment. For someone standing in the environment, this is really weird. You see a system that keeps spitting stuff at you, yeah? And while this is happening, your entanglement entropy goes down. Yeah? Because somehow the state in the environment is such that it will take these particles and build it in such that it becomes purer and purer as a function of time. And if I had shown this photo, this picture to Marcos, for example, initially, you would have said, well, you're showing me the movie running backwards, because this is a very fine-tuned situation typically where the entanglement entropy goes down. However, here, this is a very robust decrease of the entanglement entropy. You can decide to perturb the system in a time-dependent manner. As long as your system empties as a function of time, even if you shake it or do something to it, the entanglement entropy will always go down to 0. The only thing you need to make sure is that the system empties eventually, and of course that you're not coupling to other degrees of freedom that will screw things up. So this is something that basically you can only understand if you observe this, because you know the prehistory, you know that initially you started in a pure state. And so this is basically, and the reason why this is happening is that, well, as a function of time, you build up this very long-range entanglement between the particles that are in the system and that are in the environment. And then if you have a particle that's kind of going out of the system, it drags the entanglement with it and thereby reduces the entanglement in the environment that's basically seen by an observer that's sitting in the environment. Okay, we see that this semi-classical connection between entanglement generation and particle current doesn't work anymore. But caveat, it's important to realize this is, I'm talking about the entanglement entropy that's going down here, not the thermodynamic entropy, yeah? That's a different thing, yeah? It's a different thing. Okay. One other aspect of this that I kind of found interesting is that the states that you're producing in the generating in the environment, they are low energy variance states. So let me first define what I mean by this. So the kind of the environment energy variance, that's basically the variance with respect to the environment Hamiltonian. So that's just what you have in the environment. So this basically tells you about how many eigenstates you spread out the state that you have in the environment. Generically what you expect if you have, let's say, a thermal state for the variance of your Hamiltonian, it's proportional to the particle number, or for given particle density proportional to volume, which is exactly what you observe here if you look at this variance as a function of time up to a certain time, and then after that time the variance of these states go down and becomes independent of this initial system size. Oh, yeah. I haven't managed how to figure this one. Okay. So asymptotically, basically, this becomes of order 1. So you're producing this kind of low energy variance state in the environment, or putting it otherwise, someone is throwing stuff at you, and by doing that, you're spread out over fewer and fewer eigenstates. Again, this is not what you typically expect to see. And the reason is very simple. Well, the variance of the full, with respect to the whole Hamiltonian, is time invariant. That's unitary time evolution. If you wait long enough, that variance has to be equal to the variance of the environment Hamiltonian, because you don't have anything left in the system. So this must be equal. So this, for t to infinity, must be equal to this. Sorry, it should be t equals 0 here, And for t equals 0, there's just one contribution, and that's the boundary coupling. Yeah, that's why it needs to go down again. Okay, so, and well, the same kind of behavior one will find whenever one has a system that is kind of decaying into an environment. So here, this is with a PhD student. We looked at the Hubbard model, obviously using now exact diagonalization. You can't go to 10,000 lattice sites. Easy, thanks. 10,000 lattice sites. So these are very kind of small systems, and the number of states in the environment are not very large. I will try to do a bit better than that. But you see again that the kind of the number of particles in the system decays, the entanglement entropy goes up and it goes down again, and then you have finite size effect because stuff gets reflected from the boundary. So okay, so this brings me to the the summary. So what I kind of try to tell you is that the system plus environment models, they are interesting and kind of different from the generic non-equilibrium entanglement dynamics, especially if you take the point of view of someone standing in the environment. You find this robust page-life behavior, which leads to robust decrease of the entanglement entropy eventually, and that is basically driven by the long-range entanglement that is built up as a function of time. You see this breakdown of the semi-classical picture. So, or putting it otherwise, semi-classics can be completely misleading if you look at a subtle quantity like the entanglement entropy. And you generate some, I think, kind of interesting low energy variance states. So there's excited states in the environment, but they have a kind of a variance that does not scale proportional to the excitation energy. And this also answers the subtitle of the talk. So now you see why black holes are tidier than children. They create a mess at the page time, but then they clean it up again eventually. Yeah, so at some point you're back in a pure state. That doesn't usually happen with children. Anyway, thank you.
Hi, very interesting talk. Quick question. When you say m of t, which is your basically in some your system size, do you keep your m over n fraction constant?
So the maybe I need to change the notation. So n is the size of the environment.
Okay.
And that's fixed. M is the size of my system. That's also fixed.
Okay.
Initially, the expectation value of the number of particles is equal to the system size. So m at t equals 0 is m.
Okay.
And then it becomes smaller. But the size of the system and size of the environment, that doesn't change.
Okay.
Yeah.
So the only thing which is changing is just the particles.
The particles go into the environment. So typically, if you look at the numbers, let's say I have a system size that is 100, an environment that is 10,000. So that kind of, it empties out pretty well.
I have a probably very naive question. Sorry. So your entire full dynamics are unitary, correct?
Yes. Yeah.
So how is it possible that both the environment and the system see a simultaneous decrease in? How is it possible that both the system and the environment see a simultaneous increase or decrease in the entropy, because it has to be constant to the entropy of the whatever state you put in initially?
The total state is always a pure state. So basically, so you have a pure state that lives in a bipartite Hilbert space, H system, tensor H environment. And therefore, if you define the entanglement entropy with respect to this bipartition, it doesn't depend on whether you look at the reduced density operator of the system or of the environment. It always gives you the same answer, and it has to be equal. It's basically exactly the pure state that's important. Yeah. Yeah.
Thank you. Thank you for the nice talk. I was wondering, what's the difference if you just take a finite system and look at the entropy of half of the system after a quench as a function of time? Then obviously, because of the finite system, you will get re-entrances, and so you will get maximum, and then the curve.
So what's your setup? So you have a finite system.
So imagine whatever finite system you have, where you have well-defined quasi-particle, and so you use this Calabrese and Cardi picture, you divide the system into two halves and do a global quench, and then the entropy start growing linearly, and then
it doesn't go down, it just saturates.
No, if it's half of the system, of a finite system, it will never saturate, it will start going down immediately after a certain time, because indeed the particle will bounce back, and then will...
Well, I mean, but this is
so if you have a size that is smaller than half, you are right. So you will see some ramp, you will see some saturation, and then it will go down again. But if it's exactly half of the system, you would just see a cusp, and the entanglement would go down.
What you have is you can have very rare fluctuations where the entanglement entropy will go down. I mean, there is a time scale where you have recurrence. But that's not the timescale that you're talking about here.
No.
I mean, but if you have if you have an interacting system, what you describe is something I've never seen. I mean, I showed you the pictures of the entanglement entropy for the spin chains and so on. I mean, even if you divide it by half,
I can show you the numerics. So I saw it tons of time. So if you believe that there are pseudoparticles, so if you take the Ising model in transverse field, there are pseudoparticles, and you just need to take half of the chain and do the quench, and you would see this ramp, and it goes down. And it's robust because it's just that the pseudoparticle. So the pairs, now you have half of the particles on the left, on the right, after some time, they are entangled, and they start to bounce, and they start to rejoin.
Yeah. Okay, so I think what you're describing is a situation where where you have ballistic particles with all the same velocity and no interaction. You have a quadratic Hamiltonian. It's okay. If something that's like a quadratic Hamiltonian, where also in the CFT, if you have a beta ansatz, for example, where the particles are only exchanging velocities and you're not redistributing velocities, then that's something that can happen. Yes, I agree with that. Yeah, I agree with that. But that's, again, I mean, that's a class of measure zero in the space of all systems.
So thank you. A question from here. Can you comment what happens if your environment is at the finite temperature, or if your environment is observing the particles that arrive there? Will this qualitatively change or no?
So if we have some, if you are observing the state in the environment, let me think, if you're observing the state in the environment, I think what's going to happen is that, well, you are going to produce a mixed state in the environment. I mean, so you can no longer say that the entanglement entropy of the system equals the one in the environment. Yes. And the entanglement entropy of the environment will not go down to zero anymore because you've been measuring it.
Yeah, maybe to avoid this kind of entanglement measures for open systems, we can ask, maybe the easier question is, what happens if there is a thermal blob somewhere far away? Right? Will it change qualitatively as a conclusion if environment has a unitary thermal blob, right? ETH random matrix sitting somewhere?
Well, one question I can give you is if you start coupling the particles in the environment to other degrees of freedom, you won't see this behavior anymore. Yeah, because you'll start transferring the entire entanglement between system and environment to entanglement somewhere else. And if you do that, then it won't go down to zero anymore. So I think you're breaking this long range entanglement that you need for it to go down to zero. Yeah.
Okay, Stefan. When you showed us the time evolution of the entanglement entropy and of the particles, you said, well, it's surprising that the maximum of the page curve happens when there's nothing specific happening to the particles. Now, I'm not so sure. To me, it seemed, and I think it could be a sort of explanation that at that moment you have half the original particle number there.
Yes.
But isn't that also the kind of explanation that you have, that you have can have the most entanglement between system and bath, or environment when you have half of the particles on one side and on the other, because they carry the, so that something specific happens, which is half the number of particles has evaporated. But
yes, yeah. But I mean, the thing is, if you look at, let's say, the current just, there's no indication whatsoever in the current.
Okay, yeah.
I mean, in any usual quantity that you can measure, entanglement entropy is hard to measure. In any usual quantity that you can measure, you just won't see anything.
Okay, so you agree with my observation, but you say it's just not so exciting to say it's half the number of particles.
Yeah, I mean, there's nothing that behaves different from what you would naively expect. Yeah.
I think my question probably goes in a similar direction. So the model that you suggest, one-dimensional, relatively weak coupling, everything is in your system before environment is empty, is basically, in a sense, exactly your black hole model, right?
Yeah.
It seems to me still rather specific to this model that, first of all, you have a system which is much bigger than the environment. Sorry, other way around. The environment which is much bigger than the system. And that you have basically such that you can always assume that all of your population has eventually left the system, right? And so you gave a very nice and logical explanation why what you see is exactly what one would expect. And I think the devil is in the detail in that case. But how does it look like if you have more dimensions, stronger coupling, and a system that does not empty out eventually?
So I'll answer, thanks a lot. So I'll answer all three questions, starting with the last one. So, I mean, most of the numerics is done for a system that's not environment that's not infinitely larger than the system. And you can basically just put a bound on it, because you can just figure out, even if the environment is just 5 times larger than the system, you will still see it going down again. You just basically calculate how many particles will just in equilibrium be left in your system. That's just a fraction. And if it's less than half the initial number, then you expect that it has gone down again. So you can see all of this also for more realistic setups. Yeah. Then the other question was higher dimensions doesn't change anything. I mean, it's just because the physics is the same. And then what was the last question that was about?
I think it was more a statement that your Ising model is basically really exactly your black hole, right?
Yeah, I mean, you could, but you can also use interacting systems. It really, I mean, the thing is that you need something that basically that empties out a lot. Yeah, it doesn't have to go to zero. It needs to empty out a lot. And it's like, from the point of view of the system, this is trivial. From the point of view of the environment, it is weird. Yeah? Yeah?
Hi. Sorry. Thanks for the very interesting talk. I just wanted to clarify. It seems like since your system environment boundary is fixed, this is closer to an eternal black hole model. So if you wanted to model an evaporating black hole, could you change the size of the system, and would you introduce an additional term in your entropy calculation in that case?
Well, you could start playing with the boundaries. So what one is modeling here would be kind of a quasi-static situation close to the page time, where you don't have to worry so much about the event horizon shifting. But I don't claim that this is any reasonable model for. I mean, there's really fundamental differences. I mean, and that also makes it much harder to understand page curve and black hole physics than here. I mean, there's really fundamental differences. But you could start playing with the boundary. It wouldn't really change things dramatically unless the boundary follows the particles. Then, of course, things would be different. But that's not the expected direction. Yeah. Yeah.
Okay, there is one more.
To press anything? Hi, Stefan. Thanks for the fun talk. Now, at the beginning, you mentioned Kim and Hughes, diffusive energy transport, a model that doesn't have a particle transport. So my question is, have you looked at the energy transport across the interface? Because at the point when you reach the page time, from older stuff on the expansion, you realize that the energy per particle changes exactly at that point. Because you fall below half the particle number, and then you have a different emission of average energy per particle. So perhaps that could correlate actually with the page time.
Yeah, it would be easy enough to look at the expectation value of the two Hamiltonian system and environment. That's not difficult at all to do that. I just don't think it has a lot of kind of implications for it. I don't see the connection to the entanglement dynamics, but one could easily do that. Yeah, yes.
Any other question? Oh.
So maybe what would be the equivalent then of the thermodynamic entropy?
Yeah, so again, thanks. That's a very interesting question. So you would need to say, how would you want to define thermodynamic entropy here? Now, one thing is if you define thermodynamic entropy with respect, you could define thermodynamic entropy with respect to just kind of 2-point measurements, and that would agree with the entanglement entropy. You don't need to define it with respect to complicated higher order correlations, because the Wick theorem always holds. Yeah? It's a quadratic Hamiltonian. However, if you defined a thermodynamic entropy with respect to local measurements, yeah, then that thermodynamic entropy defined in this way would not go down anymore. Yeah, that would go up, and then it would saturate, and I think that's my picture. It would saturate, it would stay at that value, and the system, with respect to that coarse-grained quantity, the system would not clean up its mess. So you don't have to go to complicated higher order correlation functions, but you need to go to something that's non-local.
Okay, very nice. Any other question? Okay, so let's thank Stefan and everybody for